You can start. Yeah.
Okay. Let me share my screen. Should be this one. I think my screen should be visible right now.
Yes.
Awesome. Cool. So I'll give a short presentation on what we've done with Trident. At the start of this cohort, we set out to
Oh, by the way,
build.
we see the Google Meets right now, but is it the screen that you
Yeah,
want to show? Okay,
yeah.
nice.
I will. I don't have any slides. I'll just do a code walkthrough and like the front end walkthrough in a second. So yeah. So yeah, the idea was to build an efficient order book, giving the same experience as a centralized exchange to users, while still giving settlement guarantees with respect to zero knowledge proofs. So you could have potentially an external order matching engine that defines your rules of matching arbitrary orders, and yeah, and then the sequencing and the input outputs are all defined by zero knowledge proofs, and the settlement of all orders are defined by zero knowledge proofs as well. So this is supposed to be built as a layer 2 rollup that would settle onto Mina and would give better performance than the L1, and using the L1 directly as a liquidity layer and also a settlement layer. Cool. So we'll start with the most basic thing is how do we go about building an efficient order book, right? So we have two sides of sorry, lost my train of thought. We have two sides. We have like buy orders, sell orders, and you want an efficient order matching engine that should be able to match those orders efficiently using any. You can use any arbitrary data structure that it should be efficient both in time and space. So we start with like a simple definition of an order. In this case, we will define like an ID. Obviously, ID is going to be, in this case, some sort of either randomly generated ID or deterministic IDs in as kind of a nonce. Then you have the price and the quantity, which define the parameters for the order that's being filled, base and quote tokens that define what order pair we're working with, and whether it's a buy or a sell order, which will define how the order matching is done, and a timestamp on when the order was filled or created. Depends on how you want to use it. So we define a price level. A price level simply defines orders that are at a particular price, and the total quantity of orders at that particular price. We keep a sequential list for this because orders should be filled in first and first out for a particular price level. That's fairly standard. Then we define an order book, and this is where the interesting part starts in. So maybe I can static scale draw. About it. Okay, awesome. So what we can do is, so if we have an order book defined, and then you have like buy and sell orders coming in from each side. Let's say you have some buy orders at a variety of different price levels, and then you have sell orders at a variety of different price levels as well. Now, every time a buy order's value is greater than the largest buy orders values is less than the smallest sell order value, there should be a match and an order should be settled. So if we create a sell order here, its corresponding amount of buy orders should be filled. Oh, that's right. Its corresponding amount of buy orders should be filled. So obviously we cannot use any simpler data structures like arrays, because then even if you keep sorting them as the orders come up, as your book grows, the complexity becomes worse and worse, and it is in the size of the number of orders. Usually somewhere along the lines of, well, the best case you can do is n log n, which is not great. So what we do instead is we want to look for a data structure where we're able to find, like, track the minimum and maximum. But every time a minimum and maximum is removed from our order book, we should be able to rebalance it somehow so that the next minimum and maximum can be tracked.
Rahul, there is
Yes.
one question. If the code is public from Mahmoud, so can you share GitHub or?
Yes.
Yes.
I'll share the code after the call. Is that okay?
Yeah, okay.
But yeah, like if someone quickly wants to go and check, like it's on Aries Labs and by the name of Trident, the backend and the front end. So Trident front end. It's on our GitHub. Cool. So now we have requirements and we want to build a data structure. So how we go about it is we use something called red-black trees. Red-black trees are self-balancing binary trees that allow you to keep track of either a minima or maxima, depending on how you define the comparator. So we define two mappings. Mapping is just to keep track of buy and sell orders so that we can access them in constant time. And the prices that are existing in the order book, we define two red-black trees to keep track of the minimum and maximum buy price and the minimum sell price that exists. And then we have a base token and quote token. Obviously, for this to be deterministic, we want the base and quote token to always be in that order. So we define something called normalization, where we basically hash. Well, there's two types of normalization. The first one is with respect to the base and the quote token, and then we hash them together in exactly that order to define an order book. So like a pair's base token and the corresponding quote token hashed together is the identification of that particular order book. And then we have a price history, which we define as a circular buffer in order to not have unbounded resources. So this is done in order to still keep track of a price history that can be either fetched from an external API, visualized from an external API, or directly served to the user, whatever. However, we want only the price history existing for a certain period of time. So we define a circular buffer, which when fills and new price history comes in, it keeps on dropping from the back, so that it is at most of a maximum price history size, which for this use case we've defined 10,000 or 1,000 in this case. We also have a max number of matches, and I'll come to that, why we need that in a second, and why can't we do arbitrary number of matches in a single block that we mine. But yeah, so this is all like non-ZK code, right? We're still talking about like creating the order book, like how does the order book work? So we have very basic functions of adding an order, which adds the price tree, and adds to the price level, creates price level as well. And we also normalize the order, something called normalize order. And we do this in order to keep a standard pricing so that we can easily match prices with respect to only the base token. So how we do this is, for a sell order, we flip, like we invert the price, multiply the quantity by the price, because that would be the settle amount for the buy order. And we flip the quote token and the base token so that this becomes normalized in always the base token, the quote token. So how this works is every buy order is a price. It's in price and a quantity with respect to the base token and the quote token in that order. And a sell order is exactly the same. It's just represented in a different data structure. And now we have these orders that are represented in exactly the same token, so the base token. What we can do is we can do order matching very efficiently. And how that works is we simply find the maximum of the buy price and the maximum of the sell price, and we fill if the maximum buy price is greater than the best sell price or greater than or equal to, then we have a match, which means an order needs to be settled. In which case, we fetch orders in that particular order. In this case, like we fetch the first order, we take it out of the, or we pop it out of the orders, and then, well, we pop it here. We'll remove and delete it, and we define the matched quantity depending on the buy and like the minimum of the buy and sell quantity, and that's it. You have a matched order, right? Now you can like create a matched order. You keep on repeating it as many times as you want, as many orders you can match, right? Potentially, if we had enough orders, enough sell orders that would all sell orders were less in price than all buy orders, then like the entire order book could be settled in one single trade, in one single block. However, we cannot do that because that has it requires linear it's linear computation in the size of the number of orders that are being settled or the number of matches that are being made. So we upper bound it, but we also keep that upper bound fixed. So if we have like if we only have like one buy order and one sell order which get matched, we simply and we had 5 number of orders that need to be matched total. We take 4 orders and we match them together. We match single order and then we add 4 empty orders. And I'll come to why we need these 4 empty orders in a second. Okay, so it's fairly simple. We can cancel orders, then we can define getter functions on our order book in order to get the current book depth or the current price of the order book, price history, all current orders, best asking bid, best sell bid. Sorry, the other way around. But yeah, like you can basically get both. Sorry, you can get both the bids and the asks, the best ones very efficiently, and you can get the order book depth. You can, and this is just type of functions. Okay, cool. So now we have a highly efficient order book, which can potentially process quite a lot of orders very efficiently. See, it's like the data structure that we've chosen. It only grows in log n of the time complexity of doing any operation is only in log n of the number of orders that are being filled, which becomes highly efficient. And some benchmarking shows that we can add about 20,000 orders in our database in 28 milliseconds. Obviously, this is being done on localhost, so this would be 28 seconds plus whatever the latency is going to be for all orders to come in. But still, like it's quite fast, right? So like now we have a great order book, like very simple thing working. It's highly efficient. Now we want to do the hard part of it, which is the ZK bit. Okay, so the order book basically defines our order matching engine. And what we need to do is because like the order matching engine is quite complex and it is a lot of computation, we want to potentially do it outside of our zero-knowledge circuits, right? So all settled orders, all they care about is, were orders settled? And if they were, that should be recorded. Orders should be settled with respect to price. Obviously, we cannot guarantee the sequence of all orders at a single price level, but for now we'll assume that our matching engine is is semi-honest, and it's not going to do MEV extraction that way for now. Obviously, they can if they want to, and they will. Cool. So we want to get two guarantees. The first one being that we can show that order was settled correctly, and we can show that the price level was settled correctly. Okay, so we need these two guarantees, and we'll see how we can go about implementing them. Okay, so for the zero knowledge part, we first define the concept of an order with respect to a zero knowledge proof, right? So we define it as certain variables, something very similar to how our like order book interface looks, but in provable parameters. Okay, so we have an ID, we have a price, we have quantity, we have base token, quote token, we have a sender, we have a status, and status defines whether an order has been filled or not. And I'll come to why we define a status as well later on, and why don't we just like remove an order if it has been filled? But we'll come to that later. And then we define like it's a by function or self function and a timestamp. Right, timestamp can define either when the order was added or when it was settled. Either way, does not matter. We only need sequencing guarantees with respect to price levels. We define a very basic order ID, which is just an extension of a field. We define an order pair. An order pair defines, and it's just like a very simple class, and this is used externally, not used here. An order pair simply defines the deterministic concatenation of an order book, so that if we're trading MENA with USDT, we don't end up creating a new order book which is USDT MENA, right? It should, like, if we have a single base token that we've defined before, which is in this case MENA, that should always be MENA. And regardless of whether a user wants to trade, create a buy order in USDT, it should still be normalized and become as a sell order in MENA, or like the other way around, right? Like, because representation is the same, as long as your order matching engine's logic is correct and you have the assets. Cool. And we define an order status, which is going to be pending, filled, or canceled. Just three different values, all good. We have an order type, buy or sell order. And that's just like defines a Boolean, a true or false. True defines a buy order, false defines a sell order. We currently don't use this because we're directly encoded in the order book, but like it's a nice abstraction. It's fine, whatever. And these are just help functions here. Okay, so now the order book that I showed you outside, now we've imported it here. Now we have like this nice interface which defines our out of circuit order matching engine, right? Which we've already gone over. I'm assuming, like, for now, let's believe that this is fine, this works as intended, and the logic is correct. Okay. So now we define our order book exchange. Now, order book exchange gives you guarantees of it gives you validity proofs of settled orders, and that's basically what your zero knowledge proof is, which could be later on extended to become a dark pool, a perpetuals exchange, etc. Well, dark pool if you use the zero knowledge part, perpetuals exchange because like it is literally the same logic. It requires an order book, just the primitives are different. So you can like literally just use the same order book and do whatever. Like the only difference thing that changes in creating a new order book based protocol out of it is to change the matching logic, and that's it. Okay, cool. So we come back to our order book exchange. We define a number of matched orders, and we define a number of max matches. And these max matches, as we've hard-coded before, are 5 for all order books throughout Trident. So if Trident has 1,000 order books, this is going to be every order book is only going to do 5 matches at a time. Well, actually 10, because number of orders being matched would be 10, but 5 pairs of matches. Okay, cool. So now we define a trading pair. In this case, the trading pair is basically a deterministic version of and an approvable version of exactly what we defined here. Okay, so it has a toString method for external usage. That's fine. And then we have something called from tokens, and how we make it deterministic. So every trading pair can simply be, you can call from tokens to create a deterministic trading pair. And basically what it does is it does a conditional swap whether token A's ID is less than token B's ID. If yes, the deterministic concatenation or the deterministic identity of that trading pair becomes token A concatenated with token B. And then we have the trading pair, and we return the trading pair, whatever. And we define a hash function, hash method on this class, which basically becomes the deterministic way to, because like we don't want to keep it in this manner. We just hash them together to define a unique ID for that deterministic concatenation. And we have a simple function for conditional swap. And I think I should add a credit here because this is directly stolen from OpenJS. Okay, so now we come to the main logic, which is in this case going to be the order book exchange. We have a state with orders where we have a mapping from order ID to order. This is currently a simple Merkle tree. Ideally, it should be an index Merkle tree. Which once O1.js releases the next version, we should have out of the box. But we have a version where we've used an index Merkle tree that we've created internally at Aries as well. And on a modified version of ProtoKit. And we have registered pairs where we define the registered pairs, which define like whether it's present or not, or whatever. And then we have an order book. Well, all the order books that exist. So this is like whatever the trading pair is and the corresponding order book. And this is only used, we store it here, but this is only used out of circuit to reference to different order books. Because obviously we cannot prove map. Cool. So we have a very simple function that registers the trading pair, creates a commitment, adds a value to the registered pairs and updates, updates the commitment there. And then we add it to our out of circuit order books as well as part of out of circuit computation. We'll come to this a little bit later, and then we can do the same with, okay, actually we might want to go with creation of orders. So we sign an order, which is signed by a specific user, which we define as like the sender here. The sender is the owner of a particular order, and we define a timestamp. And timestamp is not used here for anything. It's just used for history. For it, we only keep timestamps for posterity in case anyone wants to do advanced strategies later on, depending on if they want timestamps on when orders were settled. And then we have a pair hash, which defines our deterministic order book, and then token to check and amount to check, and we flip it depending on whether it's by order or not, and we add it to the order book in orders right here. So in our order map right here, and we also add it to our off-chain order book. So our order matching engine still has like an exact representation of it. Cool. And all the normalization stuff, whatever it wants to do, it will do it by itself. So canceling an order is removing the order both from the off-chain order book and inside of our commitment. Fine. You have some getter functions to get all orders. These two different functions that do kind of the same thing. Well, actually, it's just copy of each other, which I change. You have, again, the same interface that our off-chain order book exposes. We've also exposed it here in case the user wants to access it, because we don't want to give the user access directly to our off-chain order book. And this is just a helper function to convert an off-chain order to a circuit ish order. Okay, so now comes the crux of how we match an order. And so we have a trading pair, which anyone can call a function to match an order. That's the great part about it, right? This is completely permissionless. It's not, no one defines who matches an order, right? Anyone can say, okay, I see that token in like this order book is full, and the price has tipped in either direction, which means we have potential matches, which means we can do order matching. Great, amazing. In the future, we can add a fee to it, which is paid back to the person that calls this. So there's an incentive to actually match orders in real time. Okay, so we define the hashes, whatever, and this is where we match the orders outside using our order matching engine. And this is why we had a set number of orders, right? Because a zero knowledge proof needs to do deterministic computation. A ZKVM can potentially do non-deterministic computation because you can pair it with deterministic computation at the end, but a zero knowledge proof at circuit level needs to do deterministic computation, which means we need to define the number of orders that needs to be matched every time this function gets called, which means we need to give them matched orders, whether it be an actual matched order or just being like empty orders saying we didn't match anything. It's just like an empty order, and that's fine, which will be invalid orders, so we don't need to do anything about it. We flip the prices in order to make it to reverse the normalization that we did before. And we do the zero handlings basically for empty orders because you cannot divide by zero or multiply by zero again, yada yada, irrelevant. And we return this. So like this is externally provided witness from the prover. So we have an external matching engine which we trust that it will not do any MEV extraction. So at every price level, it will give me the correct prices. So once we have that for matched orders.length, for every pair of orders, we match them. We set them as filled. We set the prices, and we do the transfers to the users for the corresponding tokens. So if I put in an order for USDT and someone put in an order for Mina, now I get Mina and they get the USDT if our orders were filled for whatever amount. Awesome. So that was the crux of how this works in essence. Currently, our journal circuits aren't that great. Hold on, I screwed something up. That doesn't look right. Okay, yes, because I think I am in group or not. Okay, it showed because no changes were done. Turbo caches the test results and showed me. So we can do 5 order matches in approximately 8.2 seconds on a MacBook Pro, which is not great, but still okay. We're getting there, right? We can still do a whole lot of optimizations here, and that's that. So that was the backend part of it. We'll go to the front end. So this is the front end. It's still not been integrated with the backend, but we wanted, like, the idea was that we wanted to build an experience that was similar to what Hyperliquid or any other like centralized exchanges provide, but still give like those guarantees. So we spent quite a bit of time iterating over what the order book is going to, order book front end and the user experience is going to look like. And this is what we came up with, right? This has been generalized slightly to show how you can extend it to, a perps text as well. Like, so you can add a borrowing rate, your funding rate, etc. You can define a perps text as well. It's exactly the same thing with like a new order matching engine, right? You can have like leverage as well on spot. You can have market orders. You can have limit orders, depending on what collateral you have. This is a feed of USDT, Mina USDT, if I'm not wrong, that is fed into TradingView, and we can directly do this to through our app chain as well, right? register through TradingView, create an external service that directly fetches the price history from our order book and keeps on updating on every settled order to TradingView. And all users that are connected to TradingView get real-time updates of their price level. And this is like what your book looks like, what the depth is. You can see a variety of different. You can see all the buy orders, the sell orders, whatever. You can see what like recent settled trades look like. You can see open orders, balances, order history, and like the idea is exactly to create a very simplified version of what you would see on a centralized exchange, similar to Binance, OKX, or whatever, right? And obviously, it comes with the Oro Wallet Magic Bundled, which means like this is only Mina compatible, right? Like this order book just works with like Mina, but like a user never knows except like signing transactions. Which in the future you could do something similar to wallet abstraction, and a user only signs in once, transfers some collateral for trading, which would be at 5,000 USDT, and that's it. Voila! You can now. Then they can do like multiple trades one by one without ever like having that one pop-up come in and say sign transaction to execute an order, sign transaction to execute an order, to actually bring centralized exchange like experience to traders on Mina. And that was my pitch.
Thanks, Rahul. Can you also have a look at the chat? I think there's few comments and questions. Yeah.
Of course. Yes. I will go through them one by one. Actually, I'll just keep sharing a screen so that if yes. So Mahmoud, the new commits are in a branch, I think, if I'm not wrong. Yes, correct. Which data structure are we using? We're using a red-black tree because we want to fetch by minimum and maximum prices, and also so that we can get price. We can efficiently traverse the tree in order of the order book depth when we want to show the order book depth. The timestamp will become a circuit constant, not change at any point of time. That would have to be witnessed. Yes, you're right. I'm a little bit confused about how to make the maximum number finding faster. Could you give me an example? There are a few ways. So we extensively did a lot of research on how real-world order books actually function, right? So there's a few ways to go about it. There is the Coinbase way, which was throw an efficient data structure at it, theoretically efficient, and call it a day, which was red-black trees. I think, if I'm not wrong, Coinbase up until 2021 was still using red-black trees in its code primarily. However, most real-world exchanges don't actually use red-black trees because it depends on what kind of order book you have. So if you're talking about a perpetual exchange, your number of orders that will settle around your current price or whatever your funding rate is, that will be less. It would be expensive to prove the red-black tree, yes, because you have to prove all self-balancing operations, which is why we do it outside. In the future, what we could do is potentially every operation we could add a constraint. So if you use an index Merkle tree, an index Merkle tree keeps every element keeps a pointer to the next larger value, right? And that's a case where we could actually prove it efficiently, because we could prove it outside and say this is the next value, and this is the next value where it should settle. And if in the index Merkle tree we find that it has a pointer to a bigger value, the proof generation fails. So we can actually prove it in circuit, right? Outside we can maintain a red-black tree. Inside we can maintain an efficient index Merkle tree, which, depending on number of orders, can be varying in height. Which Merkle trees come? Merkle trees, especially sparse Merkle trees, the representation that we use has to be a fixed height, or even Merkle trees usually have to have a fixed height for from a zero knowledge proving you wanted it to be deterministic. Yeah, that was my example. Is the UI code open source? Yes, it is. You can go check it. It's by Trident front end. Maybe I can like share the repository as well. I think that should be it. So all the current code should be in here. And if you remove the front end part, that's the Trident repository. Cool. Any questions?
Thanks, Raul, for the presentation. I think also answering the questions. So if not, I think that was the last presentation in this session. So thanks again to everyone, the presenters, O1 Labs Exploration team, and the community. So I'll see you in half an hour in the next one. See you all.
Sorry, I wanted to ask for access to the slides that were presented on this call so I can read through again for understanding. Yeah.
Sure. We'll I'll get the slides from others. Okay. All right. Bye all.